Yeah, probably somebody can write a. I'm not sure. I'm not even sure whether that interface is exposed to bots, because otherwise, somebody could potentially write a bot to stream it to YouTube. If the bot just has to talk to both Discord and YouTube API at the same time. But that can be probably problematic from the legal perspective, as far as YouTube is concerned. All right, so we are close to the starting time of the class. We got about 5-ish seconds to get started. And the stream has started already on the other side as well, on the YouTube side. And I got a private message. All right. Okay, all right, I can ignore that one for now. All right, so I am gonna get started. Time is 10:30. So I just wanted to kind of bring up the topic of prerequisite and co-requisite requirements. So you guys probably have received at least one email from me about the pre and co-requisite requirements of this class. If I reply to you and say, okay, this works, or this is good, thank you, that means you're cleared. Or on the other hand, if you have not sent me anything yet, you might want to kind of get this done over the weekend. So I'm basically making sure that everybody has the prerequisite, which is Math 372. That's the official one. But if you have taken Math 370 or anything equivalent to that, if you have taken calculus classes already, you would not have received an email from me saying that you need to show me equivalency of Math 370. On the other hand, if you have attended 4-year colleges before and you already have some kind of a degree that includes calculus, you can just give me a copy, send me a photocopy of your transcript. Okay, that's all I need also. There we go. So Aaron is confirming that with low latency turned on, it is still about 10 seconds of lag time on the YouTube side. So that means it is much better on the Discord side, because I think on the Discord side it is a fraction of a second. It's not even a second. So that makes interaction a whole lot more real time, as opposed to I have to wait 10 seconds for people to tell me that, oh, I got a question, but I have already moved on to talk about other things. So looks like Kevin is typing and has some kind of a question, so I'll wait a little bit. And as I wait, I'm going to show you something that's kind of cool. This is a preview of a markdown document that I'm editing, quote unquote, on the side, okay, which is basically just a plain text document. But it renders the content in real time, or close to real time in a browser. So it's really kind of cool, because this way I can enter equations like this, or I can just go ahead and type normal stuff like that. So I can look at this somewhat like a digital whiteboard, so I can kind of write stuff on the fly. Maybe at some point I need to go back to my tablet mode, because I need to draw arrows and stuff like that. But at least for the time being, we are good. All right, so I'm not seeing any text on the text channel of this class. Oh, okay, there we go. Okay, so Kevin replied and did not receive a reply. So I can go ahead and check it after class. So kind of stay with me after class and remind me again to check my email. Because as you guys probably imagine, I'm getting a lot of emails in the first week of class. Many of those are from people who are asking, can I still add to your class, especially the CISP440 class, which already has a wait list of 20 people. So yeah, so I'm getting a lot of those. All right, so let us continue our discussion from the other day. Oh, I'm not sure how many of you did your MBTI test, your personality test. There are a few websites for MBTI-ish kind of personality test. One is 16personalities.com, 16personalities.com, and the other one is called Truity. It spells like this. Okay, it's called Truity, and I think it's a .com. So Yep, that's it. So Truity is interesting in the sense that you can get your free assessment. Okay, they will give you a fairly good assessment, with the free one. But if you pay for one, okay, those are designed for therapists. So they're actually fairly, industrial strength when it comes to the analysis. It will give you a long analysis that is specific to you, not just your type, but specific to your answer. So it's kind of cool. They also have assessment that are specifically for career planning. So that might actually be applicable to some of you as well. So it's just another resource, not directly related to the class, but I don't think it can hurt. All right, so moving along. So last time we were starting on basic set theory already. So what we'll do is we are continuing with that topic. And I just, today I just regenerated the HTML document just to make sure that everything is up to date. I don't think the content has changed, okay? It is just the formatting has changed a little bit, okay? So last time we talked about a few things, just a really, really quick recap of what we talked about last time. The first one is if you want to list or enumerate the content inside a set, okay, you can list the content inside braces, inside what we call curly braces, okay? But braces is actually, the curly braces already, so the curly part is actually redundant. But I sometimes would actually refer to braces as curly braces, just to make sure it's clear. So these are not parentheses, okay? They're not the round parentheses. They're not the brackets, the square brackets. These are the curly braces, okay? So you got to make sure that you use the right syntax when you're trying to express what is inside a set. Now, inside this particular set, okay, the way I list the elements, the order is irrelevant, okay? All this is saying is 10 is an element, -1 is an element, 2.2 is an element, 5 is an element, 7 is an element, and 12 is also an element of T, okay? But there's no implicit ordering of any kind when we are talking about members inside a particular set, okay? We also talked about the element of, or quote-unquote in operator. It looks like this, okay? This little weird looking, E, uppercase E. That's, sometimes we call it element of. So 2.2 is an element of T. Sometimes, we can abbreviate it as just in. So we can say 2.2 in T. Now, this is not by itself a confirmation that 2.2 is in fact an element of T. It is really an operator, and it returns a value of either true or false, okay? So in the case of 2.2 in T, it is true because we can definitely find that 2.2 is inside the set of T. On the other hand, 23 in T is false because we do not see 23 as an element of T. So this is a really quick recap of those concepts. We also talked about equivalency of two different sets. So that's also something that we talked about. We talked about how a set can be itself an element of another set, just like a folder can be a component of another folder. So we talked about that as well. So now we're going to move on to section 5, which talks about then what do we do with a set that has an infinite number of elements, okay? And there are many sets like that in math and also in computer science. Now, when I say computer science, I'm going to say in computer science, with quotes. That's because in computer science, a lot of stuff that we normally say, there's an infinite number of elements, actually only has a finite number of elements, okay? When we say integers, for instance, as a type in a programming language, the number of values, distinct integer values that we can represent given a particular integer type is usually limited, okay? Because we only allocate a fixed number of bits to represent values, okay? So if you have taken CISP440, not only from me, but from anyone, you probably already understand that aspect of integers are finite, not infinite when it comes to practical programming. All right, so I'm just looking to see if there are any questions. So if you do have any questions, do not wait until I ask, do we have any questions? Okay, you can always just go ahead and type, And I see, okay, I see. I got 2 people. What stream is not available for me? Well, in that case, all right, so I'm not sure whether that concern is still valid or not, so I'm going to reply to that person. Okay, so I just replied to that person. I got one more question here. All right, so I'm going to reply to this one too. All right, there we go. So the key is I want people to kind of follow instructions. And because I think in the instructions I said send me an email with the attachment, and not using Discord. That's about the prerequisite and co-requisite check. All right, so moving on. So now the question is, how do we describe a set that has an infinite number of elements? So in this case, I use, this is going to be used throughout the entire semester. This kind of funky looking Z is referring to the set of all integers. And this kind of funky looking R is referring to the set of all real numbers. And I think these symbols are used in mathematics as well. Okay, and after all, computer science really is a branch of mathematics. So for those people who think I'm just going to be a game developer and I don't need to understand math, well, those people will be very surprised, and probably unpleasantly so too. All right, the next paragraph is talking about the set of all even integers it's also a set of infinite elements, or it has an infinite number of elements. But now the question is, how do we express it? Okay, how do we tell people, okay, that E in this case is a set of all even integers? Okay, that's the question. Now this format looks like, well, it's pretty clear, right? I mean, it's pretty clear that -4, -2, 0, 2, 4, those are all even integers. But there's no telling that this is actually a set of all even integers, because it is possible that we don't have a -6, but instead we have a -8 and an 8 here, which means we are looking at integers that are either the positive or the negative side of a power of 2. Well, we are missing 1 in that case, but you get the point. Okay, the ... is very ambiguous. It doesn't really quite describe what is in this particular set. So now what we're going to do is we are introducing a new notation. So this new notation is right here, okay, E equals 2, okay, in curly braces again, which basically means what is described inside is describing what elements E has, okay. So we have an X here and then a vertical bar. Now this vertical bar is not a bitwise OR operator. Some people look at this vertical bar as such as, okay. I will explain what it is really, in just a little bit, because it's explained right after this, okay. And then we have a description, okay. So let me see if I can highlight. No, I cannot, unfortunately. So when you look at this portion here, okay, just kind of follow my mouse pointer. So when we look at the beginning of this parenthesis and this particular close parenthesis, now what is this operator again? Let me just see if you guys did a little bit of studying, and because we talked about what this operator is. And very good. Okay, you guys actually study conjunction even better. Okay, well, not even better, but they're equivalent. They're all good answers. Excellent. Okay, I'm glad that at least some people studied. Okay, so this conjunction is basically saying, x is an element of z, which means x is an integer, and x mod 2 equals to 0. Now, what mod 2 is going to be a 0? Even integers, right? So x is an integer and it is divisible by 2. That's basically what this part is saying. So now let's go back to the vertical bar here. The vertical bar is really saying x, if and only if x is an element of E, if and only if x is an integer and x mod 2 is 0. That is what this entire notation is saying. Okay. Now note that I use the word or the phrase if and only if. instead of just if or just only if. Okay, so what is the difference, okay, between if, only if, and only if? Okay, so I think it is important to make that distinction in this class. Okay, it goes both ways. Yes, so Omar is absolutely correct that if and only if goes both ways. But what is the implication here, right? What is the implication? So let's go ahead and look at some examples of these implications. So I am going to try out my, where did I put that text editor? Oh, right there. Okay, there we go. So we are going to take a look at some examples. All right, so this is good. All right, so we'll take an example of, well, in fact, we'll just use whatever we had earlier, okay? So we'll say that x is in E, okay? But this time we're gonna say if, okay? Just using the word if. And then we use the same expression, which is x is in the set of all integers. Actually, just type it. There we go. And x mod 2 equals to 0. Okay, there we go. All right, so let's focus on this statement here. X is in E if x is an integer and x mod 2 equals to 0. Okay, in fact, I'm going to change E to something else because I don't want to confuse with the set that we are actually talking about in the notes. Okay, so we'll call this G. Okay, we'll say x is in G if and only just if. Okay, just one single if. So now if I want to look at certain elements of G, let's see which one is going to be in G. Okay, so can someone give me some examples of what you might find in the set G? Okay, so Aaron said 2. Okay, so let's check. Okay, so the question is 2 in G? And I am going to be using this word here, guaranteed to be in G. That is the question. So now you have to basically ask the question, what is the word if saying? If is basically saying it is a sufficient condition. Okay, so that means if a value of x is meeting this requirement, it is an integer, and it is divisible by 2, then it is going to be in X. So this is correct. Okay, yes, 2 has to be in G. Okay, great. So why didn't we just use if instead of if and only if? So now let me ask you this question. The question is 1 guaranteed not to be in G? That is the question, because can we just rule out and say that since 1 is not an even number, it cannot be in G, when we only use the word if? What do you guys think? Okay, so I'm not seeing any answers yet in the text channel, so I'm gonna wait a little bit for you guys to process this. Okay, the answer is yes. Okay, so Aaron has just answered no. Actually, I should say no or negative. Okay, because yes, no is kind of confusing. 1 is not guaranteed. 1 is not guaranteed not to be in G in this case. So G can actually contain 1. But why is that the case? Well, that's because 1 is not a multiple of 2. And if 1 is not a multiple of 2, then it makes this conjunction false. When this conjunction is false, then the statement of saying, x is in G if blah, 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 it doesn't apply anymore. It doesn't say anything about values that do not meet this requirement. Okay, so the answer is no. Okay, let me Forgot which window I was in. So the answer is no. It is 1 is not guaranteed not to be in G. Okay, so now we have a problem, because what about pi? Okay, so what about pi guaranteed not to be in G? And probably you guys know the answer already, right? The answer is also no. So that means G is guaranteed to have all the even numbers, but not just the even numbers. Are we understanding this part of the argument? Because this has to do with the definition of if or implies. Okay, let me represent this. Okay, so this is really saying, you know, if, okay, this is the same as, okay, in double quotes, in quotes, if, okay, I'm just gonna copy stuff here. You guys cannot see what I'm typing on the in the editor, but okay, so let's see if that sentence is okay. So we are focusing on this point here. This statement over here on the top, okay, this one here, is really saying exactly the same thing as this statement over here. Okay, I'm forgetting a and double quote. There we go. So is that okay? Can everybody just kind of accept that, you know, grammatically, if I say I don't want to say anything that is obviously not true, so I have to be careful what I'm going to say here. Okay, so I can say you can get this free toy if you order a Big Mac, okay, at McDonald's. Okay, that's the original statement. Do you think that statement is really saying the same thing as if you order a Big Mac, you can get this toy? Do they say exactly the same thing in just normal English? Yes? No? Maybe? Okay, no. Okay, so if Joshua is saying no, then I need to know, then what is the difference? Okay, so I'm going to ask this question here. What is the difference of saying y if x versus if x then y? And in both, I'm going to use double quotes. So the first question is, do you think there is a difference between these two? Y if x versus if x then y. There should be no difference, right? They really say exactly the same thing. It's just, you know, in one, we express the consequent first, and in the other one, we specify the consequent last. But they mean exactly the same thing. Logically, these two statements say exactly the same thing. Y if x and if x then y, they're basically saying exactly the same thing. Okay, are we okay with this? Okay, and Alex is typing. So. Yeah.
I'm not really clear on the Big Mac example then, because it seemed like there were other possibilities. Like, what if there were more toys?
But I'm asking whether the statements are the same. I'm not asking whether the person will get a toy or not. I'm asking whether the promise, the statement from McDonald's, is the same or not.
What about like dependency in a way? It seems like y is dependent on x. Is that?
Well, okay. The other way to look at this is if x then y is saying that x is a sufficient condition for y. Okay, so is that okay? I mean, does that kind of making any sense? If I say if you order a Big Mac, you can get this free toy, that means ordering a Big Mac is a sufficient condition to get this little toy. Yes, so if it's the same as implies, okay, so yes, so Omar is correct. So the other way, and yet another way to specify this, to look at this, is X implies Y. Yep.
I'm free until 1:15.
Okay, yet another notation this time is X right arrow Y. Is that okay? Are we doing okay so far with all the equivalent ways of saying exactly the same thing? Y, if X is one way, if X then Y is another way, X is sufficient for Y is yet another way, X implies Y is yet another way, and then X with a double bar right arrow Y is the notation that we use in mathematics. We are not touching only if yet. Okay? All right. So let me just kind of get back to the original problem of what is the problem of using just if instead of if and only if. So the problem is we cannot exclude, whoops, typo, exclude non-even integers from G using just if. There we go. Because all we are saying is what is a sufficient to have membership in G. But we are not excluding members. Okay, I'll give you this really funny example. Okay, you guys will like it. So let's talk about some really snobbish, country club, and they make this statement at the door and say, if you're a millionaire, you're automatically a member of this club. Okay. Well, all that is saying is if you're a millionaire, or being a millionaire is a sufficient condition to become a member of that club. So let's just say, one particular billionaire walks into the club and find out that, Tech, how come you are in this club too? You're not a millionaire. You're not even a quarter millionaire. Okay? And they go like, yeah, but it doesn't mean that, only millionaires can belong to this club. All it says is if you're a millionaire, you're guaranteed to be a member of this club. But there's no guarantee that other people, cannot be a member of this club. Is that okay? Okay, cool. Okay, so if itself is not sufficient, what about only if? Okay, right? Because that's the next question to ask. All right, so let's ask the next question. Now I know it sounds like we are kind of wasting time talking about these examples, but it's really super important because we are going to use implication a lot in this class. So it is important to get those concepts cleared up first. Yep, exactly. So Omar is correct about that. So that's why taking math classes in general is helpful, in this class, because now you have some additional exposure to the same concepts. And that's also partially why I enforce the prerequisite of Math 370. All right, so let's go ahead and change this statement. Okay, so this time we're going to use the set H instead. Okay, so now we say X in H, but this time we use the word only, or the phrase only if. Okay, so we use only if, and then we say X is in math ZZB. I'm just spelling out how to type this thing in LaTeX, and then wedge X mod 2 equals to 0. Okay, there we go. So now we are looking at a different set H, and the definition of H, or the way we specify membership in H, is X is in H only if X is an integer and X is divisible by 2. Okay, so do we have a problem in this case? So what is the problem? Okay, first of all, let's go back and look at the different notations. Okay, this is the same as saying if, okay, I put it in quotes here. So it's saying the same thing as if X is in H, then X is a member of the integer set and X mod 2 equals to 0. Okay. So do we have a problem with this set versus the set E in the notes? And if so, what is the problem here? Why can't we just use the phrase only if? Why do we have to use if and only if? What is the problem with this set H? Okay, so this takes a little bit of processing, doesn't it? Because I'm reversing the precedent, which is the left-hand side of an implication, and the consequent, which is the right-hand side of an implication. So I'm just flipping those two. So what this statement here, okay, let me point out which statement here. So what this statement is saying is, if you pick anything from the set H, it is guaranteed that it is it's an integer that is divisible by 2. Okay, that's all it is saying. Does it say that it contains all the even integers? It doesn't say that, does it? Okay, so if you look at the country club example, okay, this is basically the same country club. Okay, now they learn from their mistake, and now they switch the statement to say that, well, if you look at any member of our club, all of those members are millionaires. Okay, sounds pretty good, right? Well, the only problem is there may not even be a single member of that country club, and that statement will still be true. Okay, so that means H can actually be empty. Let me just write it down here. H can be empty. In other words, H can be an empty set, and that statement is still true. If X is a member of H, then X is a even integer. It is still true, the condition, the implication is still true, even if H is an empty set. It contains nothing whatsoever. Okay, so I'm gonna let you guys process this a little bit first, and then we'll kind of think about it in a slightly different way. Then it'll become clear why that is the case. I'll give you guys a clue. Look at implication as the negation of the precedent, which is the left-hand side, or the right-hand side. Okay, so A implies B is not A or B. So look at the statement this way, and I think you guys will start to realize why H can be empty in this case. Well, no, H cannot contain any element that is odd. Because if H has any element that is odd, then it will make this statement false. Okay, so we are assuming this statement is in fact true, and it is the definition of H. So any odd number will make, if X is odd, then that odd number will make that statement false. Only if doesn't mean other exclusions can't exist. Not quite sure what you're saying. I can understand every single word. I just cannot associate. I cannot link other exclusion and exist. Oh, okay. I see what you mean. Yes. So Alex is correct. Okay, now I get it. Okay. So, but what I will do is I'm going to explain this, in using the definition of implication. So we'll start with the definition of implication. No, don't worry about it. It's just me taking a little bit longer to parse that sentence. Okay, but we'll look at this from the definition of implication. Okay, so we'll say A. Okay, so
Well,
A
no, it's meant to be wielded by bears.
implies B
That's what I said. It's like
is the same as the negation of A,
it's designed to be
okay,
held by bears.
or B.
You think about this. You ever
Okay.
heard of a gorilla?
So I hope we are not too surprised by this claim, because this is actually in the notes that we talked about on Tuesday. So if this is true, then when we plug in the scenario that we have here into this particular definition, then what are we getting? Okay, so let's check it out. Okay, so now we are basically saying the negation of X is in H.
Once you're done,
Okay, and then the OR and the rest. Okay, so we'll say X is in
depends how much tranquilizer.
Z and X mod 2 equals to 0. Okay,
I don't know. Maybe.
so are we doing okay so far? Does everybody see how this sentence here, if X is in H, then X is basically a even integer? We can take this, okay, we can take this if then, okay, which is implication, use the definition of implication and convert it into the negation, the negated first part, which is X in H, and then or the second part, which is X is an even integer. Is that okay? I just applied the definition of implication. So we got 2 people typing. I'm gonna wait a little bit. Okay, so Joshua says, does the set notation always appear in that form? This has nothing to do with the set notation. Implication is what we are talking about here. Not sure what Joshua is referring to, precedence versus exclusions. I'm not specifying anything that is exclusive. I'm simply looking at the definition of implication, and we change X in H implies X is an even integer to not X in H or blah blah blah.
I guess maybe I asked the question.
Uh-huh.
A little bit weird, but from the way that I'm reading it, it seems like the first statement is you would imply that it's part of the set, but then the conditions afterwards exclude anything that wouldn't be or should show what should be in the set. So I call it an exclusion, but there's probably another word for it. Am I reading it wrong, or am I understanding the concept?
Well, okay, so in this particular example, I'm illustrating why only if is also inappropriate for what we want to express in the notes. We need if and only if, because we know, okay, in the previous example, we know why if is not sufficient, because if it's not excluding things that are not even integers. But the problem with only if is it doesn't guarantee every even integer is in H itself. So by converting the if, only if, into an implication, which is this part here, and then using the definition of implication to look at this as just a negation of something or something else, we are trying to figure out why H can be empty. Okay, so now we want to look at this particular expression. So look at this as nothing more than just an expression. Okay, it can be true, it can be false. So now the question is, what happens when H is empty? So when H is empty, what is the result of this particular expression? Are we doing okay so far? So so Aiden is typing. I'm gonna, all right. All right, so Aiden says true because X, there will be nothing in H. So no matter what x is, okay, so you can bind x to any value that you want, okay? So you can bind x to 0, okay? You can bind x to 1, you can bind x to 4, you can bind x to pi, you can bind x to tag, okay? No matter what x is bound to, okay? X is in H has to be false because I'm already telling you that H is an empty set, right? So that means if you look at x in H, this part of the entire expression is false already. What is the negation of false? True, right? So when we look at the entire negated portion of this OR, okay, this part is guaranteed to be true if H is empty. Well, in an OR, this is a normal OR, it's not an either or. So in a normal OR, if at least one side is true, we know the entire OR is true already. So that means, if H is empty, then that empty set H also meets this requirement, this entire requirement, which is this entire sentence over here. So that means H is not the set of all even integers, which is what we want. Is that okay? So one representation, which is the top one, is not excluding things, okay, that we do not want membership inside the set that we are dealing with. The other one, on the other hand, is not being inclusive enough, okay? So it is not guaranteeing that every single even number is in the set, okay? So that's why, neither if or only if is sufficient, okay? Neither of these two is sufficient to express what we want to express. What we want to express needs if and only if. So if and only if basically says, okay, if x is known to be an even integer, then we know it belongs in E. If x is not an even integer, then it does not belong in E. But it also looks at it the other way around, and we look at membership of E, then we go like, if you pick anything from E, it is guaranteed to be an integer. Anything that is not in E is guaranteed not to be an even integer. That is why if and only if is so important in this case, because as Omar said earlier, it goes both ways. The implication goes both ways, because if and only if is basically, we talked about if and only if already, right? So let's look at the definition of if and only if. Okay, x if and only if y. IFF is the abbreviation of if and only if in a lot of math context, is represented by this notation here. It is represented by a double-sided double bar arrow. So right, left, arrow, y. I think, nope, it doesn't like that. So I think the left has to be uppercase as well. Nope. Huh. Did I have a typo? Oh, maybe it's left, right arrow. So let's try that. There we go. Are we doing okay so far? Are we totally lost at this point? Okay, and that's awkward silence. Okay, someone is trying to. Okay, so I got one person with a permission issue joining the server, which means that person did not join the server early enough for me to change the role of the membership. So I'm going to do that just now. Okay. All right. Uh-oh. There we go. That's one. And let's see if I can do the other one too. All right. This is kind of equivalent to people walking into a classroom, when I'm already teaching. All right, so let me just let that person know that he or she should be able to get in now. All right, there we go. All right, so getting back to the class. Do we have any questions? I mean, I know this stuff can be confusing. Okay, so there's confirmation that we are doing okay. All right, so we will see other examples of, if and only if, if, and so on and so forth. But every time we encounter, a context, that uses implication, we have to be careful, okay? Because it sounds intuitive, but it's actually a little bit more tricky than we think. All right, so getting back to the notation in the notes. So E is, E equals to the set where every member X is a member. X is a member if and only if X is an integer and X is divisible by 2. So this is how we can define membership of a set that has an infinite number of elements, because we can now define what qualifies to be a member, or what is the only qualification of that particular set. So in general, okay, this is the general notation, is we can now define membership of a set using what we call a predicate. Okay, now the word predicate, okay, which is here, is really just a fancy word, okay, since all of you have taken C or C++ before. So you can look at a predicate as a function that returns a Boolean value. That's basically all it is to a predicate, okay? A predicate is a function that returns a Boolean value. So in this case, it only takes one single parameter, which is the element that we are trying to figure out. So P of X is a Boolean function that returns true or false. And if I use this notation here, that means X is a member of E if and only if P of X is true. So that's basically this. It's the equivalent expression as what follows here. So do we have any questions about this notation? Is really a shorthand of this notation here. And P of X can be very simple, can be something very complex, but it doesn't really matter because all P is a function that returns a Boolean value. It's either true or false. So are we good so far? Okay. Shall we move on? Okay, very good. Very good. All right, cool. All right. So now we are moving on, and section 6 talks about the empty set. We already talked about the empty set. Now, you might think the empty set is not very interesting. I mean, it is only interesting from the theoretical perspective, but it is not really interesting in any other sense. Well, the empty set is actually very interesting, as we will see throughout this semester. Okay, so the empty set is actually quite interesting. So now we can try to define operators on different sets. Okay, the first one is called intersection. So this kind of inverted U symbol is called intersection. So the way we define the intersection is A is a set, B is a set. Okay, the intersection of A and B is also a set. Now, how do we know that? Because the definition of intersection also has curly braces. Okay, so we are now trying to define what elements are in the intersection of A and B. So remember this notation here. All that is saying is E is an element of A intersecting with B if and only if E can be found in A and E can be found in B. That's all it's saying. So are we okay with this definition so far? All right, cool. Let's take a look at some examples. Okay, Aiden is typing, so I'm gonna wait a little bit. Okay, makes sense? Good. Okay, that's good feedback. So what we'll do is to take a look at a few examples. Okay, so this is what you'll be looking at while I'm typing somewhere else. Okay, so I'm going to type intersection examples. Okay, so we'll go ahead and take a look at this one first. Okay, so we'll take a look at the intersection of 1, 2, 3, and intersection is using what we call the cap symbol, I think, or maybe not. Let me look up on the side how to do that. Oh, it is the cap. It's just that oh, that's because I haven't ended the other dollar sign yet. So just give me some time to figure this out. Okay. So the other set has 2, 4, and 6 as its members. So we want to find out what is the intersection of these two. So what is the answer? And I'm going to go back to Discord and take a look at some answers. Yep, it's 2, but it's not just 2, okay? Remember, the intersection is a set itself, okay? So when you guys give me the answer of 2, and you exactly, okay, very good, Catherine. Okay, so the intersection itself is a set. Okay, now even if that set only has one element, you have to use braces to indicate that this is a set and this is the only member of that set. Okay, so that is important in terms of notation. So let me just give the answer here. Okay, so it is just 2 by itself in a set. Okay. All right, so let's try some more examples. Okay, so let's take a look at this one. So we got 1, 2, 3 again as the first set, and this is the intersection with 4, 5, 6. And so in this case, what is the answer to this question? Yep, very good. Okay, I like all the answers. All of those answers are correct. It is the empty set. Okay, so let me type it in my answer here. There we go. Very good. Okay, so I don't want to see anyone saying that the intersection is 0. Okay, even though there are some people who use something that looks like a 0, as a notation of the empty set, I do not use that symbol in this class. So in this class, if you want to express the empty set, you have to use curly braces with nothing in between. Okay, I don't want to see people saying the intersection is false. Okay, it is not a Boolean. Okay, the result of an intersection should be a set itself. It is not a Boolean value. It is not an integer. It is just going to be a set. Okay. All right. So let's go ahead and take a look at another example. So now we have 1, 2, 3 as a set, and it is intersecting with this guy over here. So what do you think is the answer to this question? It is, come on, go ahead. Yep, there you go. All right, so that is the correct answer. Anything, in fact, anything, if you try to find the intersection of anything and the empty set, it's going to be the empty set. Okay, very good. Okay, so I think we're getting this down. Okay, so that is encouraging. Oh, how about this one? Okay, let's try something that is a little bit more confusing. So let's try this one. And Well, since I'm trying to make this, tricky, let's make it like super tricky. What about this? Okay, let's see if you guys are getting thrown off by a set inside a set. Good job. All right. Indeed, it is the empty set. It is the empty set because the set of 1, 2 does not match 1, okay? Because 1 is not a set, so 1, 2 does not match 1. And 3 does not match the set 2, 3 either, because 3 is just a single value, but 2, 3 in curly braces is a set. So those two cannot match either. Very good. Okay, so I think we are getting the idea here. Just one more. Okay, I'm just going to give you guys one more. Oops, too many. What about this one? Oh, okay. I'll address Sandeep's question a little bit later. So let's focus on the last one first. I think you guys will like this one. Not quite, Omar. You're getting close. Nope. Remember, the intersection is a set itself. Yes, Catherine. Okay, Catherine has gotten it. Okay, so it is the set of a set of the empty set. There we go. Okay, so that is the actual correct answer. There we go. Nope. Catherine has gotten it and John has gotten it. Those two are correct answers. I mean, the second answer from John is correct. All right, so let's go back to Sandeep's earlier question. So he or she typed, what if we have the set 1 in... Oh, can't type fast enough. Yep, it takes a little practice with all those curly braces. But let me show you what I have to type to get what you see on the screen. This is actually what I type off the screen. This is called the markdown notation. And the specific thing that will generate the math equations, this stuff over here, is called the LaTeX or just TeX format. It looks like TEX, but it's actually tau epsilon chi. So that's what I'm typing on the side to kind of generate all of these equations. Okay, so let me get back to Sandeep's question. What if we have the set of 1 in the set of 1? Oh, that's intersection, I see. Okay, so the lowercase n is intersection. So in that case, okay, I can just type it, in the virtual whiteboard. Okay, so let's take a look at that one. So the set of 1 intersecting with the set of 1 and the value of 2. Okay, all right, so let's figure this out. There we go. Okay, so what do you guys think is the answer to the last row that I have just put up on the virtual whiteboard? Yeah. So now the question boils down to, is 1 the same thing as the set with 1 in it? The answer is no. So nothing matches, right? So if nothing matches, what is the answer? It's the empty set. There we go. All right, very good. So are we still doing okay so far with the concept of the intersection of 2 different sets? All right, very good. All right, so I'm looking at the time, and this is probably a good time to tell you what the key is today for row taking. And please do not forget to do that, okay? If you forget to do it, I'm going to drop you. And now, this class has room, okay? If you got dropped, I can add you back in. But the point is, I will do what I said I would do. Okay, so just kind of keep that in mind. So I'm gonna give you guys the key, okay, and I'll even put it into the virtual whiteboard. It's part of the video. Okay, the key today is cardinality. Cardinality is basically a fancy word to say how many things is in a particular set. Okay, that's cardinality. We talked about cardinality on Tuesday already, okay, but I chose to use it as today's role-taking key. So you might want to head over, to get that done now. I'll give you guys a little bit of time, okay? And as you guys are doing it, I'm gonna set up some examples. Okay, cool. It's good to see some confirmation that it's already done, because I don't know how long it takes for you guys to switch over to Canvas, go into the activity, type in cardinality, press the enter key, make sure you get the point, and then come back here. Cool. All right. So now we're going to move on to unions. Okay. So the next set operator is called a union. And when you look at the union operator, it looks almost the same as intersection. In fact, if you look at intersection, it's kind of like an inverted U as a symbol, as the operator. And then union is really just kind of like a U, as an operator. And then when you look at how they're defined, they look almost exactly the same as well, because one is using the AND operator, and the other one is using the OR operator. So a quick way to, or an intuitive way to look at union is basically to say A union B is a set. Okay, so begin with a set. It is a set where an element belongs to A union B if and only if that element is found in A or that element is found in B. Okay, so it can be found in just one of them or both of them. It doesn't really matter. Okay, so let's go ahead and take a look at some examples. Okay, so we'll take a look at some union examples, just so that we get a good understanding of that operator. All right, so let's go ahead and, in fact, I'm just going to be super lazy and copy and paste some stuff from earlier. Okay, and instead of using a intersection operator, I'm going to use a union operator. There we go. All right, so what do you think is the answer to this question? 1, 2, 3 as a set, union with 2, 4, 6 as a set. Now this one looks kind of straightforward, but it does have one tiny teensy little trick to it, okay? But it's not much. Yep, Catherine is correct. Wait, hold on a second here. Doesn't make sense, right? Because 1, 2, 3 has 3 elements, 2, 4, 6 has 3 elements. How come the union doesn't have 6 elements? How come it only has got 5 elements? I like how Aiden is jumping on the explanation right away. It's like, cool. But this is not Jeopardy, so we are not competing for time here. Exactly, good job. Okay, 2 is in both sets, but when we specify elements in a set, it has to be unique. Okay, so 2 appearing only once really has nothing to do with how union is defined. It has to do with how a set is defined, where each element, each value can appear only up to once as a member in a set. Okay, we do not repeat elements. Okay, very good. Okay, so those are all very good explanations. So that means, let me give you the answer over here. You guys have it already in Discord, but I just want to put it here for completeness, for the video. There we go. All right, very good. So just like last time, we're gonna try something with an empty set. Okay, so we'll throw an empty set example into here, change the intersection to a union, and now what would be the answer? Good job. Yes, that is indeed the answer. Okay, the set of 1, 2, 3 is the correct answer in this case. In fact, if you take any set and you union it with the empty set, you get the original set back. In other words, if you think about the union operator like addition or plus in normal arithmetic, and you look at the empty set as the value of 0 in normal arithmetic, they work out the same way. Okay. In other words, you can look at the empty set as the identity of union in basically set algebra. Okay, so I'm setting you guys up, for those of you who need to take abstract algebra, I'm just kind of setting you guys up for that particular class that you will take in the future. Okay, so it's not related to stuff that we are talking about right now, but it does have a future direction if that is where you want to go. All right, very good. So now we move on in our notes again, okay, because we are now done with union. So now we look at what looks like subtraction here. So A minus B, A is a set, B is a set, okay? A minus B is also a set because we see the curly braces here. But an element is in A minus B if and only if it is found in A but not found in B, okay? So that's how we quote-unquote find the quote-unquote the difference between two sets, okay? So are we doing okay so far with this? Now, as I said in the previous lecture, I encourage all of you to open up your own browser and basically have your own browser to synchronize with what we are seeing here on the projector so that I can switch back and forth without you losing track of what we are talking about. Okay, so I'm hoping that you guys can look at the definition, on your side, on your own browser when I switch to the examples. Okay. So we'll take a look at some examples about, I will call it difference, okay, in quotes. Okay, so these are examples. All right. So the first two examples are confusing. Okay, so I'll show you exactly why it is confusing. So the first one is a set A. So A is known to be a set. Okay. Minus the empty set. So what do you think is the answer to that question? How do you describe a set where each element of that set, an element is in A minus the empty set if and only if it is found in A but not found in the empty set? What do you think would be the answer to that question? Yep, those are all correct answers. Good job. Okay, so the correct answer is just the set A itself, okay? Because the empty set contains nothing, right? So if the empty set contains nothing, then if I ask what are the things that I can only find in A but not in the empty set, oh, well, that would just be the set of A itself, okay? So that's kind of the interesting thing, okay? So let's reverse these and find out what the answer would be. Okay, so the empty set minus A. Oh, I forgot about the backslash. So there we go. What do you think is that answer? I'm not even telling you what A has. Okay, but yep, exactly. That is just the empty set. Okay, very good. Okay, so I think we're getting the concepts. But I'm just going to give you guys maybe one more example. So we got 1, 2, 3 again, minus 2, 4, 6. And what do you think is the answer to this question? Yep. All right. Good job. Yep, it is just the two members, 1 and 3, because 1 and 3 are the ones that we can find in the first set, which has 1, 2, 3. But 2 cannot be part of the answer because 2 is also found in the second one. All right, cool. So getting back to the notes, okay. So the next one is a little bit interesting. It sounds like it's not very useful, but it really is useful. So this one is also interesting in the sense that the things that is in the result of the operation doesn't look exactly like the same things in either one of the the sets that are providing values to the operator. Okay, this is called the Cartesian product. So the Cartesian product is defined like this. Okay, so when we look at the elements of A Cartesian product with B, then each element can be described as xy in parentheses. Okay, these are not curly braces, in parentheses, xy, if and only if x is found in A and y is found in B. Okay, so now we need to explain a few things notation wise. When we see this symbol here, okay, xy in parentheses, it is known as a two tuple. It is not a set of xy, it is a two tuple. A tuple is a container, kind of like, set being a container, but there is a big difference. Well, there are two main differences. The first difference is ordering is important inside a tuple. So that means 1, 2 in parentheses is not considered the same as 2, 1 in parentheses. Okay, so the tuple. So tuples are really kind of like arrays. Okay, if you think about arrays in just about any programming language, a tuple is kind of like an array. Okay, so ordering is important. And then the second thing is you can have identical values in different positions inside a tuple. In other words, if you are looking at a two tuple, the word 2, okay, the number 2 in a two tuple simply means it has a length of 2. It is a tuple with a length of 2. A tuple, once again, is an array. So a two tuple is really saying the same thing as an array with 2 elements. Okay, but you can have the 2 values within a two tuple being exactly the same. There's no problem with that with a two tuple. Okay, so the definition of A Cartesian product with B is it is a set of 2 tuples where the first item of the two tuple has to come from A and the second item of the two tuple has to come from B. That is the definition of a Cartesian product. So now I'm switching to the electronic whiteboard and we'll go through some examples and see if we can figure these out. I'm looking at time, we got about 8 minutes, which is good. Okay, so we are making good time. So now we are looking at Cartesian product examples. Okay. So we'll go ahead and reuse some of the examples that we have done already. So we have 1, 2, 3, and then we have the times, symbol. And then we got, let's say 2, 4, 6. Okay, this is it's going to be a little bit long, okay, but I think, it's not a bad example to look at. Okay, so you guys only have to give me like just a taste of what is in this set because there are 9 elements and each one has 2 items. So it's going to take you guys quite a bit of time to type everything. So just go ahead and give me, a few examples and then just do ... okay, if you want to. Unless you can write a program to do this in less than 30 seconds. Okay. Yep, so there are a few systematic ways to do it. You can say 1. So you basically pick 1 from the first set. Then you can pair 1 up with 2. You can pair 1 up with 4. Then you can pair 1 up with 6. Then you choose the second item in the first set. Now ordering, I know ordering is not important, but this is how we can make things kind of systematic. So we got 2, 2, 2, 4, 2, 6, and then we got 3, 2, right? 3, 4, and 3, 6. So if you count, there should be 9 elements. in the result in the Cartesian product between 1, 2, 3 and 2, 4, 6. Is that okay? Is that concept, understood? Okay, all right, looks like it is okay. But it is important to see how 2, 2 is a legitimate 2 tuple as a member of the Cartesian product. Okay, it's perfectly okay. Let me see what Aiden is typing. All right. Oh, okay, so let me take a look. All right, so John's notation is incorrect because those curly braces, okay, let me just kind of put it in Discord, okay? Need overall curly braces and use parentheses for individual items. Okay, so if you're on Discord, you can see my feedback. So I didn't see that. So Aiden is very, very observant and saw the minor differences, between the notations. So that is correct. So Aiden is 100% correct that when it comes to the notation, Catherine was the only one who got the notations right. But most people got the concept right, okay, but not the notation. So, but it's very noteworthy to mention that because parentheses are different from braces. Okay, they mean different things. One means membership in a set, and the other one is used to denote content inside a tuple. All right, very good. Good job, Aiden. Thank you. Because I'm not known to pay attention to fine details, unfortunately. Okay, let's check out a few other examples. Okay, so we have a set A. I don't even bother to let you know what is in it, and I want to find the Cartesian product between A and the empty set. So what do you think that's going to look like? Remember, everything in a Cartesian product has to be a 2 tuple, where the first thing comes from the first set, or the one to the left, and the second thing has to come from the second set, which is the one to the right-hand side. So what do you think is the Cartesian product between any set A and the empty set? Sandeep is correct. Okay, it is just the empty set. Okay, it doesn't matter what A is. Okay, but because everything in A has to pair up with one thing in the other set, which is the empty set. But guess what? The empty set has nothing. It contributes nothing. So that's why the Cartesian product between any set and the empty set is in fact the empty set. Okay, so let's look at yet another one. Okay, because I do want people to understand that this can happen. Okay, what about a set being? What about the Cartesian product of a set and itself? Okay. Well, first of all, can it happen? Well, I don't see how it cannot happen, right? So now the question is, what is in this particular one? Now this one, I think you guys can enumerate because there are only 4 things within this Cartesian product, so you can enumerate every single thing inside the result. All right. Yep, so you guys are all right, okay? But since I like to be different, I'm gonna choose a different way to represent this thing, okay? I'm just gonna go for some really wacky order. All right, so you guys are very systematic. I can see that you guys are very, very systematic, where you pick the first value listed in the first set, okay, and then you pair that up with everything in the second set. Then you move on to the second value of the first set, and then you pair that up with everything in the second set. That's perfectly okay. Okay, it's a very systematic way to get things done, and it's good. Okay, But my answer looks kind of randomish, but it's actually not incorrect either, okay? Because within a set, ordering is not important, okay? As long as we see the same 4 elements as the result of the Cartesian product, it's fine, okay? Very good, okay? So we are making really good progress today, and I like that. Let's see here. So we are going to stop here because we are running out of time today. It's already 11:49. So we are running out of time, and I'm actually double booked during this time. I have a meeting that started at 11:30. So I'm going to head over to the other meeting, but I'll still be keeping an eye on Discord to answer questions. So I will continue to be double booked for the time being. But what I want you guys to do is to finish this module first. Okay, so finish basic set theory as a module. We only got like 2 or 3 more concepts to go, which is subset of, proper subset of. Okay, so those are the only 2, and also the cardinality. So we only got a few concepts left in this module.
I don't think they should have shot him at all.
But before next Tuesday, okay? So this is why I do not like Tuesday, Thursday classes, because between Thursday and Tuesday, there are 5 days, okay? So you can look at 5 days as, oh, we got plenty of time to review the material, but the realistic question is how many people actually review the content over a weekend, right? So if people are not reviewing the content over a weekend, over 5 days, then next Tuesday, for those people who actually did not do any reviewing, did not watch the video again, did not go through the notes again, those people will be kind of lost, right? So I want you guys to keep reading, okay? So I want you guys to finish reading basic set theory and move on to basic quantifiers, okay? Now, basic quantifiers is a relatively short module, so you might want to continue on to read set theory using quantifiers before next Tuesday, okay? And I'm going to release, no, I take it back. I'm not going to release the set theory homework assignment, not yet. And I forgot to mention I forgot to give you the answer to the ungraded assignment for the Morgan's Law. So I will go ahead and do that in just a moment. But other than that, we are done with today's lecture. Uh-oh, Discord just crap out. Okay, I did not realize the Discord just kind of crapped out. There we go. Am I in? Okay, I apologize. Discord is just kind of crapped out. So I'm back, but the screen is not being shared. I just want you to make sure that everybody knows what to read over the weekend. So it's basic quantifiers and set theory using quantifiers. Yeah, so thank you. Yeah, it's time to go anyway, because it's already 11:50, but Discord crapped out just before I was ready to say goodbye to you guys. So have a nice weekend, okay? The weather is nice, the smoke is dissipating, but just don't forget to kind of keep an eye on this class, okay? So that's just one little thing to remind you guys to do. All right. And I'm gonna see what you guys have to type. Oh, okay, sure, you're welcome. The wonders of technology. Well, that's why Discord is hiring. Yep, a lot of companies are not doing well, but Discord is hiring big time. What positions? Let's head out there and find out. Discord job. All right, so I'm going to post it here. So they have business development, communication. They're both in, all the jobs are in San Francisco, of all places. Huh? Senior graphic designer. And then lots and lots of positions in engineering. So they have core engineering manager, data infrastructure engineering manager, data products engineering manager, machine learning engineering manager, product engineering manager, lots of senior software engineers positions as well, one opening in marketing, and 2 openings in offices. No internship. Well, I don't think they would ever advertise internship positions, but it doesn't hurt to send them an email and ask them, right? So Omar, if that is what you're interested in, you can go ahead and kind of just go ahead and ask them. It certainly cannot hurt, right? But it costs a lot of money to live in San Francisco, so yeah. And then we got some feedback from Omar. I'm not sure about that, John. It depends on what position you get into. Yeah, if you can ever intern with Facebook or Discord or anything like that, that is a big item on your resume. That is really good.
Waiting for nighttime in Monster Hunter World.
All right, I'm just gonna keep an eye on these, typing, but I'm gonna have to go in maybe another few minutes. All right. It depends on the position. So when you look at office manager, I'm not sure how much office managers are paid. I'm clicking on it.
Jack, did you end the YouTube stream? No, you didn't. YouTube stream.
YouTube stream should still be going because I didn't stop it. Yeah, that one should still be going. Has it stopped already?
No, I was wondering if you intended it to keep going.
Yeah, it's fine. Yeah, but thank you for the reminder. Yes, so Rick, go ahead and send me another email. I thought I replied to every single one. So if I have not replied to yours, that means I must have missed it somewhere.
Power.
Yep.
Sorry. Power.
Yeah, working in San Francisco can be expensive, and there are a few other things where it's kind of tricky too. Working in San Francisco. All right. So I am going to be rude and disconnect myself from the voice channel because I kind of have to head over to the other meeting at this point. But I will still be participating in the text channel whenever I can. So I'm gonna get myself out of the voice channel for now. Oh, you too. Thank you. Everybody have a nice weekend and enjoy the nice weather without the smoke and relatively cool as well. So it's gonna be a nice weekend. Yep. Well, you can do it outside. Do Calc 2 outside and enjoy the good weather.